Okay, so we've just calculated this first naive distance, the edit distance, and we get 0.3. So what does it mean? It's our approximation of what we want to get. Remember that we want branch length to be expressed in units being the expected number of substitutions per site. So here we see that this expected number of substitution could be 0.3, okay? Because here we have 3 sites where it's supposed that there has been 1 substitution and amongst 10 sites. Okay, but we'll see that this distance is not really sound from the mathematical viewpoint. This distance has some shortcomings. First, all mutations yield the same distance. So it doesn't matter here whether it's been a mutation from G to A, a mutation from G to T. It has the same, all mutations have the same contribution to the total distance. But from a biochemical standpoint, we know that some mutations occur from a physico-chemical viewpoint more easily than others. For instance, transitions, so mutations within purines from A to G or from G to A is more easy to achieve from a physico-chemical viewpoint than transversions. So transversions would be from A to T, or from G to C, or from G to T. Okay, transitions are within purines or within pyrimidines. So we would like to account for this fact and to give a lower cost for mutations from for transitions than for transversions. Second point is that here what we say, if we say the distance is 0.3, is that we say that, okay, from sequence 1 to sequence 2, there is a time that is 2t, and during this time 2t, there has been, for instance, on the site number 4, only 1 mutation from G to A, if we go from sequence 1 to sequence 2, or on the reversed path from A to G. Okay, there has been only 1 mutation. So here the common ancestor was either G or A for site number 4, and it evolved to the other nucleotide on one of the 2 branches. That's the assumption. Okay, that's why here we count only 1 mutation. But it's an underestimation of the true evolutionary history, because it may be that, for instance, when we see this G to A, it may be that, in fact, along the path of length 2t, there has been 1 mutation, for instance, from G to T, and then 1 other mutation from T to A. For instance, it may be then that the nucleotide present on the site number 4 in the most recent common ancestor was T. Okay, and it has evolved to G on this branch, and this T has evolved to A on this branch, which gives you 2 mutations for this site number 4. Okay, so this is an underestimation of the true number of mutations to say that every time we observe a site with 2 different nucleotides, it corresponds to only 1 mutation. Okay, so here I give 2 examples, A to G to T. We see an edit distance of 1 between A and T, but in fact the true distance in terms of evolutionary events of mutation is 2. Here we have what we call a silent mutation, double mutation. It's possible that A evolved to G and then G evolves back to A. So we count an edit distance of 0, while the true distance in terms of evolutionary events is 2. Okay. There is also something that is distances and date the most recent common ancestor in million years. So that's the prime of calibration. Okay. Here, if we say that the branch length is the expected number of substitutions per site, or the probability that there is the expected number of substitutions per site. If we say this, if we here, for instance, we see 0.3 is equal to 2t with this naive distance, so t is equal to 0.15. This is a number of expected mutations per site. If we have no idea of how fast these mutations take place, we don't know how to scale this in terms of evolutionary time, in terms of million years. Okay, we need to have more information and estimate of how many mutations per year or per million years in average, and if we have this information, then we can translate branch length in terms of average number of mutations per site into real biological or geological time. Okay, so in order to address these different shortcomings of this simple edit distance, we'll have to design more accurate models of evolution. And let's have a break here.